Thank you very much for the kind introduction. Just one small adjustment. I'm not a doctor yet. I'm still working on that. So I'm still a PhD student and hopefully a doctor to be soon in a few years. So yeah, it takes quite a long time. Yeah, Professor Adam couldn't be here today, but he's very sorry to not be here. But I'm grateful for the opportunity to present some of the research which he and Dr. Markiewicz have been doing for the last 30 years or so in the area of geotechnical, of geothermal energy. And I will focus today on energy geostructures, but have a few introductory words about the general concept of geothermal energy first. So we heard a little bit about climate impact of civil engineering today already, and we all know these 17 UN goals. Why did I list them here? I believe that the geothermal energy area has to do with several of these UN goals. Most importantly, number 7, affordable and clean energy, but also in the area of infrastructure, sustainable cities and communities, responsible consumption, and climate action. So the construction sector is a huge emitter of CO2, we all know that, but also the building sector itself is a large CO2 emitter, simply by heating and to some extent also cooling our buildings. And geothermal energy is one way we can meet our climate goals, or at least approach them. So I want to focus on shallow geothermal energy because, as you probably know, there are a lot of different areas in geothermal energy. And at our institute, we focus on shallow geothermal systems, mainly, but not exclusively, closed-loop systems. And I will talk talk about those in a minute, and especially on energy geostructures. I will talk a little bit about the characteristics and peculiarities of these structures and about our focus of research. And I'll finish with some long-term monitoring data from the Leinster Tunnel and of the field-scale energy pile tests. So first, if we talk about geothermal energy, we have to ask ourselves, is it even possible to meet our demands, to use the system to cover our heating and cooling needs? And for this, a study was done in 2010 for Austria, where some universities and research departments looked into the potential of geothermal energy. And what came out of that research was basically most of the country could fully cover their heating and cooling needs with just shallow application of geothermal energy, so the first 100 meters, without direct use of groundwater. There are some areas like Vienna, Graz, Linz, Salzburg, and Innsbruck, like the urban, densely populated areas, where not the full demand could be met, but then again, if we look at other sources as well, deep geothermal energy and so on, we could probably cover all of the demand. So, if we talk about using geothermal energy, we have to have a brief understanding about how this system could work. So, I'm just gonna briefly introduce what we are talking about today. We have this primary circuit here. This is what interests us. This is our ground, which usually has a relatively stable temperature from 10 to 14 degrees, all the way down to 100 meters or so. Only then the temperature increases slightly, 1 degree Celsius, for example, or approximately for every 100 meters. So if we have a liquid, for example, in some tubes which have 0 to 4 degrees Celsius, we already have a delta T of 10 degrees Celsius. This, of course, is usually not enough to heat our homes, so we couple that with a heat pump. We need some amount of external energy for that, in this example 25%, and then we can elevate this temperature to higher levels and use this. Of course, there are different systems we can use, and I'm gonna try to categorize those here. So when I started, I tried to wrap my head around all the different systems to make sense of it, because in the literature there's quite a few different names and like explanations for different systems. So I tried to have a look into what is what. So we have here shallow geothermal systems. In Austria, we say that's up to 300 meters depth because of mining and water laws. Could be different in other countries. And closed systems here. So with closed systems, I mean we put some tubes in the ground or in some structures. Here, for example, in some piles. And we circulate some heat exchanger fluid in those pipes. And we can use different structures, different kind of piles. We could use some barrettes, some wall elements, diaphragm walls, pie walls. There are a lot of different ways we can use this system and extract energy from the ground, also inject energy into the ground. We can also use base slabs, of course, but also tunnel slabs, lining segments. So, and all these structures which are underlined in blue here is what we call in German Massivabsorber. So it's basically thermoactive concrete structures. So the pipes are embedded in concrete. And these have some positive effects. This has some positive effects on the heat exchange. Of course, there are also other methods as well. So at TU Wien, there were some research projects in the early 2000s concerning some energy anchors and some geotextiles for tunnel purposes, but also for dam constructions and so on. And these are all what I would call energy geostructures. So this is obviously very well termed by Professor Lallouis as well, who wrote a famous book about this. What I would say about energy geostructures is that the most important thing is they are synergistically used. So I would have needed those elements in any case for another reason. And I use it secondarily for energy extraction or injection. Of course, there are other systems as well, horizontal collectors, sewers, the borehole heat exchangers, which are a lot more common, of course, in shallow geothermal system, but which also can go deeper than 300 meters. And then we have some open systems like wells, open water usage, or deep geothermal energy. Okay, so here I drew a fictitious metro station just to illustrate that basically if we have a large building, or any building in that case, with earth, with some structures which are in contact with the earth, we basically can use all of the parts as heat exchangers. So basically the entire station could be used if wanted. So what are some characteristics of energy geostructures? I already mentioned that. It's the synergistic use. So I would have needed to build this anyway. The elements are very robust, and by that I mean once the concrete is poured and the heat exchanger pipes are embedded in the concrete, then I see no possibility of them really getting damaged. So they will probably last as long as the building itself, 50, 100 years. And then the efficiency. So due to the concrete, the concrete has really high mass, and the activated volume is pretty large, and the thermal properties of the concrete help us with the heat exchange. So it becomes more storage, also in contrary to borehole heat exchangers, which use the ground. There are some differences to borehole heat exchangers, and I mention this because most of the geothermal systems used are borehole heat exchangers and shallow collectors. This is a statistic of Switzerland from 2021, where we can clearly see that only 1% of the geothermal energy is extracted by energy geostructures. So borehole heat exchangers are pretty much a 1D element. I can rather easily calculate the energy extracted from them. Energy geostructures, on the other hand, I usually have to model in 3D with numerical simulations. And I always have to consider the static requirements, so it's the secondary use, as I said. And then again, in energy geostructures, most of the elements used are energy piles. This is, I think, because in those kind of elements, the pile is the easiest one, so it's basically a ball heat exchanger with a larger volume. But other elements like tunnels and walls get more complicated. Okay, I quickly want to talk about operation schemes. So how can I use these systems? Usually I will couple that with a heat pump. So, for example, I have 80% of my energy coming from the ground, some external energy in form of electricity, usually. And that would mean, in this example, a coefficient of performance of 5, which is a pretty average level nowadays, I would say. I can also reverse this whole operation and use it with a cooling machine. Same principle. But more interesting is the direct cooling or free cooling. So I don't use a cooling machine, I just circulate the water inside the pipes, and this is a highly efficient way to cool your building. The same could be done for heating as well, which is, well, it wouldn't be warm enough to heat your home, but you could use this system for ice preventation of platform ramps, roads, bridges, and so on. And one topic we want to examine closer in the future at the Institute is direct heating with solar storage. So the idea is basically to take solar energy, heat up the ground over a few years, heat it up to pretty high temperatures, and then use direct heating without a heat pump. This is also interesting in the context of energy networks, which are low temperature networks in urban areas. Okay, I'll just briefly go over this. So if we have energy geostructures, we always have to think about what are the effects of the thermal load on the elements. So first of all, we of course have additional stresses if the expansion is restricted. And if it's not restricted, then we of course have some additional displacements. And I have to take this into account. Also, at some extent, we have a reduction in cross-section. If we take a pile, for example, so if we have a large pile, 1.20 meters here, I think, the reduction in cross-section is pretty negligible. But with some smaller piles, like these driven piles, it could become important. And in our mind, the most important thing is the interaction between the elements and the ground itself. So if we have some freezing in the ground, if we have some freezing in the ground, we could alter the interaction, the interface, and have also some heaving effects due to that in some soils. So this is usually to be prevented. How are the norms and the guidelines for this? So a few countries have put out some guidelines regarding energy geostructures, some only for piles, some for other elements as well. Of course, Switzerland was one of the first countries to do this. I don't want to go into detail, but because the Eurocode, the next generation, was mentioned today as well, there will be one annex on this, but it's very briefly mentioned there only. So we would need some more guidelines and some more norms for practitioners how to deal with these interactions. One reason why geothermal projects are usually not getting realized is that they are integrated into the project too late. So some planning has already been done. Then people think, oh, we could use the system, but then it's sometimes already too late because you need to plan all this very early on. You need to know where the connection pipes are going to be. You need to know where the distribution block will be, room for some technical rooms for the heat pump and so on. One example where this was really well done was the art center in Bregenz, not so far from here. And this is an interesting example because by using these energy piles and diaphragm walls with a heat pump, and also some concrete ceilings and wall elements in the building itself that are activated, you generate a really nice climate condition, stable temperatures, stable humidity for the art collection. Of course, all this doesn't get easier in tunneling, but there are some good indications on that in the Austrian guideline written by Roman Markiewicz, if you want to have a closer look on that. I want to focus more on my topics, on the long-term experiences. So first I'll talk a little bit about the Leinster Tunnel in Vienna. And then I will talk just briefly about the metro station Tauberstraße and the research project Unteres Hausfeld. So what was the Leinster Tunnel project? It was a railway project in the early 2000s in Vienna, one of the largest railway projects today, with a long urban tunnel. The section we are looking at in the west of Vienna, HT23, was constructed as a cut-and-cover tunnel, a top-down method, with an intermittent pile wall. And this is important because back then there were no real experiences with energy geostructures in tunnel applications. So what my supervisors and Professor Brunner back then also did were to use the experiences they had from the building sector, from the high-rise buildings, and use it in this tunnel section. So the energy extracted from the tunnel was used to heat a building, a school building close by, from 2004 to 2022. And the building has now been demolished last summer, but that's good for us because now we can measure what we call regeneration phase. So we get the data without energy operation. In total, there were 59 energy piles. Every third pile was equipped with heat exchangers. This was done to have no or little effect of the piles to each other, so that they don't interact too much. In total, 250 meters of energy of tunnel was activated, and what is important, it was only used for heating purposes. So it was not used in the summer to cool the building. And this is a crucial point because usually you want to have both so that the ground can regenerate. So you use the ground basically as a storage, as a battery. But in this case, there was only only heating. So the question was also, would that be possible over a long period of time? Because this was very new, the Institute put numerous sensors in the elements. So most importantly, this is the measuring pile, where there were at 5 different levels, combined extensometers, strain gauges and temperature sensors, and on 5 levels, on the earth side and on the air side. So on the air side, of course, I mean the side towards the tunnel, which below the slab is of course also surrounded by the ground. We are here in the Fluge, so it's a very how is it called? Weathered rock, basically, with not really any groundwater movement, and the groundwater flow would be from the other direction and is pumped below the tunnel section anyway. So groundwater is not the biggest factor here. So there are some additional piles which have temperature sensors, and of course we measure also the air temperature, the inlet and outlet temperatures, and some other data. So first, this is here the energy data. I don't want to spend too much time on this, but just a comparison. If borehole heat exchangers would have been constructed instead of this, 16 to 21 boreholes would have been needed with 150 meters each. And the new school now, which is currently built, will use those, and the construction company told me that 31 borehole heat exchangers were constructed. This is probably due to the building getting larger. So this is the data over the whole the data series that we have. So this is, I believe, the longest data series on energy geostructures in the world. And I just want to point out a few things. So we can clearly see some mild winters, and in the last years we have only mild winters. But then again, the inlet temperature, so the temperature coming from the heat pump going into the piles, decreased after some years, and it was below 0 degrees in the last years. So this is usually not what we want. And also the difference between inlet and outlet temperature increased. And if we look at the temperature data in all the piles, we can see that the pile temperature dropped as well. And also in the beginning, all the temperatures were basically the same in the winter, but in the last year, it was pretty scattered. So some piles were pretty warm, some were pretty cold. And why is that? We believe that there was no maintenance done on this entire system for the whole 19, now 20 years. And that's due to some air trapped in some of the circuits. Some of the circuits were not flown through very well or at all. So this means there's a decrease in efficiency. Some of the piles have to work that much harder to compensate for the others. And one indication for that are these photographs. So this is how we found the technical room when we entered in 2021. And you have some massive icing of the water outside the pipes. But not all of them. So here you can clearly see that some are frozen, but not all of them, which indicates that those which are frozen are flown through pretty well, have a good flow, and the other ones not at all or diminished flow. So this, of course, could be avoided if maintenance would have been done and de-aeration would have been done. The strain data is, I just want to say, basically the order of magnitude of strain didn't change at all during all these years. And if we look at the regeneration phase here at the end, where the system was not operational, we see that the strains are basically half of that of the operation phase. So it's the impact on the structure itself is not that huge. If we pick out one of the years, 2005, 2006, we can plot the measurement data from here. We clearly see the school holidays. We can also see that there's a full regeneration, and this is true for all the years. So at the end of the heating season, the temperature is basically back to where it started. So yes, the system functions very well without cooling. This is the inlet and outlet temperature. And we see here the difference inlet-outlet, 4 to 5 degrees Celsius, which is recommended, and the difference between the pile temperature and the inlet temperature. And this is now the new data with the regeneration phase, and we can clearly see the effect that not using the piles has. So below the base slab, which are these two, the green and purple one, are pretty much constant throughout the year, unlike before. And the other measuring points above the base slab are influenced by the air temperature in the tunnel. And this is the newest data for the last months. Okay, so the effect the energy operation has on these tunnels, or this tunnel section, is approximately 5 to 8 degrees in total. So this is not a huge deal. And in general, generally speaking, energy operation is a serviceability issue, if any, and never really a ultimate limit state issue. So we had a master thesis, excellent master thesis from Nathalie Sagasser this year, and she modeled this tunnel section with COMSOL multiphysics, firmer model. And the first question is always about the boundary conditions of these systems. So with an energy pile, it's pretty straightforward. That's usually the easiest one. But with tunnels and walls, it gets more difficult. I think Professor Lalui had a nice talk about this. This can make and break a project, because you usually, at the beginning of a project, you don't really know the tunnel temperature, which will be present, and also the airflow. And usually we have a convection boundary condition inside the tunnel. In our case, we didn't know that. We don't have sensors for that yet. We hopefully will get some. So we use the fixed boundary, fixed temperature condition as well in the tunnel, where Natalie did some really nice work to approach the real temperature. Okay. So the results are here. Without any energy operation, you can clearly see that the pile below the base slab is approximately the ground temperature, and the whole system is governed by this tunnel air side. With energy operation, of course, it's different. The pile has pretty much the same temperature in all the depth. And inside the pile, if we look at cross sections, we can clearly see the effect of the inlet temperature, which goes around like this, coming from colder, looping up and down the pile, and getting warmer by that. So if we look at the results of the numerical simulation, we can plot this for our year 2005-2006 and get these results. And if we plot on top our measurement data, we can see this fits perfectly. So we want to use this model in the future to look at other years, to look at the regeneration phase, and also to be able to predict the behavior of future tunnels. Okay, just very briefly about the second long-term measurements I'm still doing. This is from the metro station Taborstraße. And I don't want to go into details here, but just so much the system here is a lot more complicated, just because well, at the Lancer tunnel it's not that simple either, but it's basically one pile wall and straightforward system. Here we have different systems altogether. So we have diaphragm walls which are activated, the bottom slab as well, the piles, and the tunnel slab. And all of this is interconnected, and it's hard to analyze the data with measurements just taken at certain points. But yes, we measure those, the diaphragm wall here since 2008, and have some really nice data as well. Okay, so the last topic is the thermomechanical behavior of energy piles. We were, of course, not the earliest ones on that. I think Professor Lalui did some pile tests early 2000s, also in London, in the US, and in Australia, and many more places. But there are some aspects to our pile test which are quite unique, I think. So we are located here in the east part of Vienna. And the research project was not about energy piles only, but it was to test various foundation elements. So you can see here in the two test fields a whole lot of different elements were tested for typical ground conditions in Vienna, which are sandy gravels and Miocene sediments. So the energy pile tests there were two piles equipped and tested for several months with different diameters and lengths, one of each in each like typical soil layer. And I want to focus on the Miocene sediment one today. So the goal was to investigate the influence of the thermal loading on the load displacement behavior of the energy piles. And my job now is to look at the data and to numerically model this as well. So what was first done by Dr. Markiewicz was to model this whole thing thermally in COMSOL to set up a test procedure, so to know how long which phase should last and what load should be used. Then the piles were constructed, and what is unique about this, that in this middle section here, a double steel tube was used so that the shaft friction would only develop in this lower area, which is where the Miocene sediments are located. And also the heat exchanger tubes were concentrated in this area. So they were simply passed through from the top and then looped only in these lower sections and passed through again. And the load was a dead load, so that no load fluctuations would occur during those months. The system was well equipped with numerous sensors, strain extensometers, strain gauges, radial strain gauges, and a lot of temperature sensors, of course, and also some fiber optic cables. And I just had a look on about them last weeks, because we just got those from the city of Vienna. And I had a look at on the temperature data of this, and this is plotted here. So you can clearly see the effect that this looping only in the bottom section has on the temperature inside the pile. So yeah, the inlet temperature for the heating case was 35 degrees. And phase 1, for example, was a heating case. You can see here the temperature rising. Then the temperature was set to 2 degrees for the cooling case. And phase 1 and 2 had 600 kilonewtons on top, and phase 3 and 4 had 800 kilonewtons on top. And again, here with 35 and 2 degrees Celsius. In the end, I should mention in phase 6, a static pile load test was done, and the results were compared to other piles nearby without any energy use. So here on the left we can see the mechanical load, and on the right side the thermal load as well as the pile temperature. So the blue line would be exactly the plot we had before. And what's interesting here is if we look at the purple line here, that's the temperature in the ground in 1.75 meters away from the pile axis. And it's already very small. So we can conclude from that in these type of soils, the energy operation doesn't really affect much of the ground, even after several weeks or months, as the simulation showed as well. These are also some results that were concluded from the pile tests in London clay, I believe. So the pile head displacement is plotted here on the left bottom side, and on the right side is the strain. And we can conclude from those that the pile was pretty free to move, and this is with a typical serviceability load on top. So it would need a very, very much higher load on top to restrict the movement and to generate more stresses in the pile. Finally, the static pile tests were conducted, and you can see here the 5 of the tests done on ordinary piles. And if we plot on top the energy pile, it's surprising that it's that much higher. The load displacement behavior is that much better of the energy pile. Well, our theory is that by the cyclic preloading during the earlier phases, the ground around the pile was basically preloaded and pre-compacted, and then when the final load up to 5.5 meganewtons came, the displacement behavior was that much better. It's not that much better for the other pile, for the pile in the grabber sediments, which would be just marginally better than the other ones. I have to look closer into that as well in the future. Okay, with that I'm nearly finished. Just some 3 takeaway points. Geothermal systems have been proven for decades, so the long-term measurement data we have indicate no problems with these systems at all. And there are numerous different systems that can be used. So in for any construction method, or building type, you can basically activate some of the parts. And in my opinion, it will be helpful, well, if we come back to the climate topic, that in the future, if there are any buildings constructed in the from the public domain or public from public shareholders, that geothermal energy should be at least investigated if it's feasible and not the other way around. My personal outlook, I want to continue on the long-term measurements, which are of course then used for verification of models, and also to help with the design of future buildings. And I also want to have a closer look on the thermomechanical modeling of those structures, especially of the piles numerically. One or two research focus for our institute will be the development of a planning tool, a simple planning tool to give a quick and easy way to see if the use of any type of geothermal system is feasible, and especially for Vienna at the beginning, and also to look in the aforementioned heat storage option with the solar heat or excess heat. Thank you very much.
Thank you very much for the very interesting presentation. Maybe we have time for a couple of questions. Are there any questions? Yes, back there. Adonia, there. Kostas.
Thank you very much for your presentation. I want to ask something about the slide 40.
40?
The previous slide, actually, the pilot test.
Yeah.
Maybe I didn't understand it well. All the lines have different pile loading of different piles, which are similar. The piles are the same. I ask about the scatter that we observe here in your lines.
So if I go back to the ground view real quick. So there were a whole lot of piles tested. I believe 5 of each type. So different construction methods, 5 piles, different soil layers, 5 piles, and the 5 piles which are identical in construction method and soil layer, like in the Miocene layer, are the ones which are displayed in the graph. So they are the same diameter, same length, everything is the same except for the thermal load.
So I don't understand in this slide again, the 40, the lines should be the same, or the scatter of all the scatter comes from different soil properties, so from loading.
You mean why they are not exactly the same each time?
Okay, let's say it's a scatter. This is the first part of my question. The second part of my question is, because you conclude that because of the thermal loading, you have a better response because of cyclic loading. Do you have an estimate of how much is the strain that the soil receives due to this cyclic loading in the pile?
Okay, for the second one, I don't have this answer yet, no. And for the first, if I understand correctly, you mean that there are differences in the conventional piles. They are not exactly the same, right?
Yes.
Well, you will always have some differences in the piles, right? So they are close to each other, but not exactly. You will have some differences, but they are pretty small, I would say, if you look at the total pile load displacement behavior. So there's just the one basically which is much smaller than that. Of course, if we tested more energy piles, this would scatter as well. But in our opinion, they would always perform a little bit better than the conventional piles.
Thank you. Thank you very much.
Yes, here.
Same question. The normal piles were also retested after this period of time, or was it just the energy piles that were retested?
Retested, you mean the conventional payload test?
Yeah, if I understood correctly, all the piles were tested at the start, and then these energy piles were tested again after some heating, cooling time.
Okay, no. The conventional piles were just tested with a conventional payload test, and the energy pile had these phases with heating, cooling cycles, and was then tested until failure at the end. And those are the results of that.
But then you have no comparison. If you initially would have tested the energy pile, it could have already shown this.
Yeah, but we can't really test the pile until failure and then do the tests and test it again, right?
Yeah.
So that's not really possible, in my opinion. Because we have, with 5.5 meganewtons of load here, we already have pretty large displacement. So this is where the pile failure was concluded.
So what is a mechanism? What is a cyclic loading because of a thermal cycles doing, and it increases the strength?
So I think the radial expansion is pretty small in comparison, but the actual loading is much higher, deformation or strain. And for that, I think that the pile load, the pile base gets basically compacted by this cyclic load. So this is just a theory, of course. We have to look closer into the data. That's why I'm not a doctor yet. But we hope that we can examine this further in the next.
But it looks like that you have an increase of a shaft resistance, not only of a tip.
Well, basically, it's I would say it's mainly the base resistance, but also the shaft resistance. Yes, but I would say the base resistance contributes more to this, if I have it correctly here. But yeah, I will definitely look closer into this.
Very interesting. Is there any other question at this moment? Okay, a last one, Laurent.
Thank you for the very nice talk. I think it's more comment. I think that Professor Lalui studied this kind of cycle stuff, and as far as I remember, it's a long time ago already, he realized that there is no significant bearing capacity increase due to the geothermal pile.
Okay. Yeah, that's possible. That's well, I just have this data here from our test, and this was one theory. Of course, it's a theory. Maybe there are some other factors at play, of course, which can explain this increase in load behavior or load displacement behavior, or this better behavior.
It's very interesting that from your entire talk, Kostas initiated this, and all the discussion is on this slide. Okay, let us thank once more our speaker for a very nice presentation.